Welcome back, everyone. Um, uh, in this lecture, we're going to talk about, we're going to start off on our discussion of Chapter 7, which is called Quantum Statistics. And it really is the place where we take the statistical mechanics that we built up in the previous chapter, and now we're going to push those into the regime where quantum mechanics and quantum mechanical effects are crucially important. And so to do that, we're going to start by building up another tool, an extension of the idea of the Boltzmann factor that we used in the previous chapter. So we're going to again embed our system in some sort of ambient environment, which we call the reservoir. Out here, we can describe our system as having an energy and a number of particles, and our reservoir has a thermal energy and a number of particles, and can be described by quantities like the temperature or the chemical potential. So this interaction between our system and its environment, when we looked at this in the previous chapter, we allowed the system and the environment to exchange energy, but nothing else. Now we're going to relax that a little and let the system and the environment also exchange particles, and examine what happens if we do that. We're not going to explicitly investigate what happens when you allow the system and its environment to exchange volume. In other words, we're not going to look so much at the enthalpy effect. We're going to concentrate primarily here on the exchange of particles and the generation and annihilation of particles and how that plays into the thermal physics, because at least at the quantum systems that we're talking about, the volume effect doesn't tend to be relevant, or if it is relevant, isn't particularly significant. So we're going to, again, allow our system to exchange energy and particles and keep track of what happens then. Sort of building off of the idea we had beforehand, let's look at the ratio of the probability of finding our system in two different states. So the relative probability of finding our system in state 2 versus the relative probability of finding our system in state 1. And again, the thermodynamics is dominated by the desire for the environment to maximize its entropy, and so the relationship, or the ratio of probabilities here, is just going to be the ratio of the multiplicities of the reservoir for those two states. In other words, we allow the system changes between state 1 and state 2, and that has some effect on the environment, and the relative probabilities of those will be dominated by the relative probabilities, or the relative multiplicities of the reservoir, and that in turn is going to give us if we turn these multiplicities into entropies, then we can write that as E to the entropy of the reservoir at state 2 over Boltzmann's constant K, divided by E to the entropy of the reservoir at state 1 divided by Boltzmann's constant K, where we basically inverted the definition of entropy here to get that result. And thus, we can say that the relative probability is just E to the entropy of the reservoir at state 2 minus the entropy of the reservoir at state 1 divided by Boltzmann's constant K. And since the reservoir is going to be much larger than the system, we're going to be able to approximate any exchange of entropy or any changes of entropy due to particle exchange and energy exchange as small, so that we can use the differential version of the thermodynamic identity and say that the change in the entropy of the reservoir is 1 over the temperature times the change in the energy of the reservoir plus technically PdV, the change in the volume of the reservoir, minus chemical potential dN of the reservoir. And since we're allowing, again, energy exchange and particle exchange, those two terms will remain. But again, for the reasons I said before, in these quantum systems, we're going to ignore the volume change. And that means that our change in entropy here between state 2 and state 1 is just 1 over the temperature times, well, the change in the energies, or the differences between the two energy states, minus the chemical potential times the number of particles in each state. So that our relative probability then here becomes probability of S2 over the probability of being in S1 is e to the minus energy of state 2 minus chemical potential times the number of particles in state 2 over kT, and e to the minus energy of state 1 minus the chemical potential times the number of particles in state 1 over kT. So these things are looking a bit like Boltzmann terms, Boltzmann factors, but they're not quite Boltzmann factors. We've replaced the Boltzmann factor with something we call the Gibbs factor, which is a factor that looks like e to the minus energy of a state minus the chemical potential times the number of particles in that state over kT. So we've replaced the Boltzmann factor with a Gibbs factor, but we proceed basically with the same logic we did in the previous chapter. This gives us a probability, once we normalize things, of being in state S. So once we normalize, we say the system has to be in a state somewhere, so we normalize all the probabilities to 1. That gives us a absolute probability of 1 over a function z here. It's a slightly scriptier version of z in the textbook, but basically still another version of the partition function, e to the minus Gibbs factor and that this scripty version of the partition function, called the grand partition function, is again just the sum of over all the states of all the Gibbs factors now, as opposed to Boltzmann factors. So E of S minus mu n of S over kT. And it's the inclusion of this chemical potential term which really defines the difference here between Boltzmann statistics and the quantum statistics with the Gibbs factors that we're going to be using here. So this thing is called the grand partition function, or sometimes also known as the Gibbs sum. There's an ensemble of all of the possible states associated with this grand partition function called the grand canonical ensemble, and so on. If we have a system which involves more than one kind of particle, then we can adapt our Gibbs factor to include a chemical potential term for each of the chemical species, each of the particle species in our system. So a chemical potential term for species A, and a chemical potential term for species B, and so on and so forth, until we've accounted for all of the chemical or all of the species that we have in our system, and again just divide by KT at the end. All right, so that is sort of the tool we need to now take the concepts we built up in Chapter 6 and start applying them in a more quantum mechanically oriented context. So the first thing we're going to look at is the example that the author gives in the textbook of considering a single oxygen molecule, an O2 molecule, binding with a site on a hemoglobin molecule. So we're just going to schematically represent that. Here's our site, and the site can either be empty. That's one of the states of our site, in which case it has energy 0, or the site can be connected to an O2 molecule, in which case it's got an energy of roughly minus 0.7 eV, which he calls this quantity epsilon. So there's two states of our system. It's either empty or filled, and those two states have two different energies, and so it's relatively easy to write out our grand partition function here as, well, what is the Gibbs factor for our first state? Well, the Gibbs factor for our first state is the empty state, in which case the energy is 0 and the number of particles is 0. And so this is just e to the 0, or 1. And the Gibbs factor for our second state is e to the minus epsilon minus mu over kT. So this is the energy of that state. This is the chemical potential associated with that state, and divided by kT. So there is our grand partition function with two terms, one for the empty term and one for the occupied term. So this is the empty state, this is the occupied state, and our partition function needs to be, or is just the sum of those two terms. The energy term is trivial. We know what the two energies are, but to to move forward, we got to know what the chemical potential is for our oxygen state. And so, well, if we're talking about a hemoglobin molecule in the context of our lungs, well, those hemoglobin molecules have to be in chemical equilibrium with the oxygen, or the air in the that we're breathing, and so the chemical potential in our filled state has to match the chemical potential of oxygen in our atmosphere. And so we can use the ideal gas result that we derived last time, that the chemical potential in an ideal gas is minus kT times the log of V over N times the interior partition function and the quantum volume VQ. And your book does a little bit of hand waving and just gives us an answer, but I thought we would actually go through and see where the value here for the chemical potential comes from. So we have a partial pressure of oxygen in the atmosphere of something like 0.2 atmospheres. So pressure equals 0.2 atmospheres. We have essentially 20% oxygen in the Earth's atmosphere, and PV equals NKT. So that's the ideal gas law. And so applying the ideal gas law here, we can solve for this first term. The V over N term is KT over our pressure. And in this case, K is the Boltzmann constant, so 1.381 times 10 to the minus 23 joules per Kelvin. And he works at 310 kelvins, which he says body temperature. It's a good enough estimate for body temperature. And we're going to divide that here by the pressure, which is 0.2 times 1 atmosphere, which is 1.0, technically 1.01 times 10 to the 5 newtons per square meter. And if you take all those things, 1.381, 10 to the minus 23, multiply by 310, divide by 0.2, and divide by 1.01, 10 to the 5, then you get a partial pressure here of, or sorry, a V over N here, a value which is 2.14 times 10 to the minus 25, and that's cubic meters, because this is a volume per particle or volume per molecule. So that's the amount of space basically an oxygen molecule, a single oxygen molecule in our atmosphere would be expected to take up. The next thing we can evaluate here is the quantum volume. So the quantum volume, again derived last lecture, is Planck's constant over the square root of 2 pi times the mass of our molecule times kT cubed. And so in our case, that's, we're going to go ahead and put bracket around that. We got 6.63 10 to the minus 34 joule seconds, Planck's constant, on the top. And on the bottom, we're going to put everything in a radical sign. So 2 pi, the molecular weight of oxygen, that's 2 atomic mass 16 atoms, or 32 times the atomic mass unit, 1.67, 10 to the minus 27 kilograms. And kT down there, so 1.38 times 10 to the minus 23 joules per Kelvin, and again 310 Kelvin, take the square root of that whole thing, and then cube this whole mess. So 2 times pi times 32 times 1.67 10 to the minus 27 times 1.38 10 to the minus 23 times 310. That's on the bottom. Take the square root of that thing, invert it, and multiply it by 6.63, 10 to the minus 34, and then cube that whole thing. Whoops. And what we get is that our quantum volume here is 5.3 10 to the minus 33 cubic meters. So we've evaluated V over N, we've evaluated quantum volume. The only thing we have left to evaluate is the internal partition function. So if we're talking 300 Kelvin, that's relatively close to room temperature. And the kinds of shenanigans that we're going to tend to see for a diatomic molecule like oxygen is mostly rotation. Vibrational modes would tend to need to be hotter. Electronic excitations would certainly tend to need to be hotter. And so the kinds of stuff that we're going to have to take into account here is mostly the rotation of our diatomic molecule. So in the previous chapter, we looked at the rotation of diatomic molecules and said that the partition function for a diatomic molecule where we have indistinguishable particles is at reasonably highish temperatures like we have here going to be kT over twice the energy associated with those rotational energy levels. That characteristic energy, E rot here, is h bar squared over 2I. So this is Planck's constant squared, which is 1.05 times 10 to the minus 34 joule seconds. Square that. 2 on the bottom, and I here is the moment of inertia of oxygen. So let's go look that up. Here we have the National Institute of Standards and Technology database of chemical data. Here we have oxygen 2, diatomic oxygen, and we're looking down here for the rotational constant, rotational moment of inertia, and it says that our moment of inertia here for O2 is 1.95 times 10 to the minus 39 gram centimeters squared, and that is, thankfully, a moment of inertia. So that's the moment of inertia, but let's translate that into MKS units here. So that's going to be divide by 1 kilogram is 1,000 grams, and 1 meter is 100 centimeters. Square that. So that's going to be 1.95, 10 to the minus 39 divided by 1,000 and divided by 10,000 gives us 1.95 times 10 to the minus 46 kilogram meters squared for the moment of inertia. And so we plug that in up here, 1.95, 10 to the minus 46 kilogram meters squared. And if we chug through that, that gives us a rotational energy here, 1.05, 10 to the minus 34 squared divided by 2 divided by 1.95, 10 to the minus 46. And that gives us 1.05, 10 to the minus 34 squared divided by 2 divided by 0.95, 10 to the minus 46. Our energy here of 2.8, 10 to the minus 23 joules, and we're just going to write that in terms of EV here, so divide by 1.6, 10 to the minus 19, and that gives us, so this is our rotational energy level here is about 1.8 times 10 to the minus 4 EV. Which means then if we plug all of these things, or if we plug this back into our partition function, then is KT, which is going to be, let's use the Boltzmann constant also in terms of EV. So that's 8.617 10 to the minus 5 EV per Kelvin times 310 Kelvin over 2 times 1.8, 10 to the minus 4 EV gives us 8.617, 10 to the minus 5 times 310 divided by 2 divided by 1.8, 10 to the minus 4. Gives us a number here about 74 or so is our Z interior. So now we can then evaluate, where to go? We're over here. Our chemical potential then is minus KT times the logarithm of V over N, which is 2.14 10 to the minus 25 cubic meters, times our internal partition function 74, divide by our quantum volume 5.3 10 to the minus 33 cubic meters. So times 2.14 10 to the minus 25 divided by 5.3 10 to the minus 33. Take the log of that. This is minus KT times 21.8 or so. And so our chemical potential is minus, again, let's use the 8.617 10 to the minus 5 EV per Kelvin, 310 Kelvin, and 21.8 So 310 times 8.617, 10 to the minus 5. And this gives us a chemical potential of minus 0.6 eV, which is indeed the answer our book gives us. But in this, he goes from here's the partition, or here's the chemical potential here, to here's its answer. And other than mentioning briefly the 0.2 atmospheres and the 310 Kelvin body temperature, he doesn't really justify this statement at all. And we went and dug it all up using previous results, and it takes about a page and a half or so to work through that. So there we go. What does this chemical potential get us? Well, that means that the Gibbs factor for the occupied state, e to the minus energy minus chemical potential over kT, we can write this down as e to the minus, our energy was minus 0.7 eV, our chemical potential is minus 0.6 eV, and kT here. So our Gibbs factor then is e to the 0.1 eV over kT. So that's e to the 0.1 eV divided by 8.617, 10 to the minus 5 eV per Kelvin, and 310 Kelvin. So 8.617, 10 to the minus 5 times 310, invert that, times 0.1, e to that, gives us a Gibbs factor here of about 42 or so. That's the Gibbs factor for our occupied state. What this means then is the probability that our hemoglobin site is occupied. That's going to be the Gibbs factor for the occupied state, 42, over the partition function, which is just the Gibbs factor for the occupied state plus the the Gibbs factor for the unoccupied state, which is 1. So this is 42 over 43, or 0.98. So 98% of the hemoglobin sites will be occupied. And your lungs will work as they are supposed to. The oxygen from your lungs will wind up in your bloodstream, and that's a good thing. All right, so then he says, but what if we allow a little bit of carbon monoxide in there? So what if carbon monoxide is present at the rate of 1 carbon monoxide molecule per 100 oxygen molecules? Well, now how does this change things? Well, first of all, our system has gotten more complicated. There are now 2 types of molecules. There are two states that there are now 3 states that our system could be in: empty, filled with an oxygen, or filled with a CO molecule. And so our partition function then becomes 1 plus the e to the minus energy of the oxygen state minus the chemical potential of the oxygen state over kT. But now there's a term here, e to the minus energy of the CO state minus the chemical potential of the carbon monoxide over kT. So there's this extra term to deal with. The energy of the carbon monoxide state, well, the carbon monoxide binds a little bit harder to the hemoglobin, so it's minus 0.85 eV rather than minus 0.7 eV. How does that affect our chemical potential here? Well, the chemical potential, remember, if we come back here, our chemical potential is minus kT times the logarithm of V over N. The interior, in this case, rotational partition function, and the quantum volume. All right, so what's changing here? Well, V over N, that's just the volume per particle. And so that changes in this case because the number of particles is down. So V over N for carbon monoxide is going to be 100 times V over N for oxygen, because there's fewer carbon monoxide molecules by a factor of 100, and this changes our volume here by 2.14 10 to the minus 23 cubic meters. Equivalently, this is also essentially saying that the partial pressure of the CO is down by a factor of 100 from the partial pressure of the oxygen. The quantum volume, well, that's going to change because the molecular mass changes. And so our quantum volume here becomes, well, again, it's h over 2 pi mk, or square root of 2 pi mkt. So we still have our 6.63 10 to the minus 34 joule seconds. And on the bottom, we're going to have 2 pi. Now our molecule is a 16 plus a 12. So oxygen and a carbon times atomic mass 1.67, 10 to the minus 27 kilograms. Boltzmann's constant 1.38, 10 to the minus 23 joules per Kelvin, and a temperature of 310 Kelvin. Take the square root of that whole thing on the bottom and cube this whole mess. And if you do that and work through it, it comes out to be the quantum volume for carbon monoxide, 6.5 times 10 to the minus 33 cubic meters, as compared to 5.3 10 to the 33 cubic meters for oxygen. Apparently, carbon monoxide takes up a little bit more room than the oxygen does at the same temperature. We also have to recalculate our rotation. And so, first of all, well, that's going to mean we need to look up a moment of inertia for carbon monoxide. So here we have the same source, looking for carbon monoxide, moment of inertia of 1.45, 10 to the minus 39 grams centimeters squared, which is 1.45 10 to the minus 46 kilogram meters squared. And our rotational energy here for carbon monoxide, again, h bar squared over 2I, and 1.05 10 to the minus 34 joule seconds squared over 2 times 1.45 10 to the minus 46 kilogram meters squared gives us an energy here. I'm just going to write it in EV of 2.4 times 10 to the minus 4 EV. Again, slightly larger than the rotational energy for O2. And then our partition function for the CO, the interior partition function for the CO, well, CO is a diatomic molecule, but you can distinguish the two molecules. It's carbon and oxygen. So our rotational partition function here is just kT over our rotational energy. So 8.617 10 to the minus 5 eV per Kelvin times 310 kelvins over 2.4 times 10 to the minus 4 eV, and this turns out to be about 111. So then we plug everything into our chemical potential minus kT times the logarithm of 2.14 10 to the minus 23 cubic meters, 111 on the top, and a quantum volume of 6.5 10 to the minus 33 cubic meters. And this all comes out, when you plug it all in, to be a chemical potential of minus 0.71 eV. So that our Gibbs factor then for the carbon monoxide term becomes e to the minus, again, minus 0.85 eV minus a negative 0.71 eV over kT. And you work through all this, and I get a number closer to 189, which is a little larger than the number he gets. Rounding and all that business in here, slightly different data. But the basic result here is that the occupied by O2 is still a partition, or still a Gibbs factor of 42, but now 1 plus 42 plus 189 on the bottom gives us an occupation more like 0.18 or 18%. So just a little bit of carbon monoxide dramatically reduces the occupation of our site by oxygen molecules in favor of the CO2 or the carbon monoxide molecules. So a little bit of carbon monoxide starves your blood of oxygen super fast. Okay, so moving on from this example, let's get to the meat of where we're going with this. So we saw with the ideal gas law that for indistinguishable particles, we had this partition function that looked like 1 over n factorial times the initial single particle partition function to the n. And the problem is that when we get to the quantum limit, when the particles start crowding each other, this approximation breaks down. And so to illustrate that, he starts with a very simple illustration. He says, imagine we have a system where we have 5 states and 2 particles that we want to distribute into those 5 states. Well, if we can tell the difference between the 2 particles, if they're distinguishable, this is easy, right? If it's distinguishable, then the number of then our partition function is just 5 times 5, or 25, all right? But when they're indistinguishable, like we had up here, well, this result would imply 1 over n factorial z1 to the n. Well, our z1 is 5, so this is 1 over 2 factorial, or just 1/2, 5 squared. So that's 1/2 of 25 is 12.5 states. So clearly, this doesn't work so well down when we've got discrete states to deal with. And so we need to think a little bit more carefully about where things are. And he draws this thing. He says, well, let's just go ahead and label them. We're going to label as 1 a state which has 1 particle in it, and label as 0 a state which has no particles in it, and label as 2 a state which has 2 particles in it. So those are the only options for each of the states. So we have 1, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, and 1, 0, 0, 0, 1. Those are all the states where the first state, or all the ways that we could have the first state be occupied with 1. And then there's a 0, 1, 1, 0, 0, and a 0, 1, 0, 1, 0, and a 0, 1, 0, 0, 1. And then we keep going, move that first one over, 0, 0, 1, 1, 0, 0, 0, 1, 0, 1, and then there's 0, 0, 0, 1, 1. Those are all of the single one particle at a time possibilities. And then if we allow 2 particles in a box, then you also have 2, 0, 0, 0, 0, 0, 2, 0, 0, 0, 0, 0, 2, 0, 0, 0, 0, 0, 2, 0, and 0, 0, 0, 0, 2, right? So there are, if we only allow 1 particle per box, then there are 10 possibilities at 1 particle per box. And if we allow 2 particles per box, that is another 5 if 2 per box allowed. Right? So either 5 or either 10 or 15, neither of which is 12.5. Right? So counting up the states by hand leads to this possibility. And this distinction between whether or not we allow particles to share the same state, or to be in the same state, depends on the kind of particles we have. And indeed, there are 2 distinct kinds of particles that we find in quantum mechanics. Bosons, which have integer spin, so 0, 1, 2, 3, spin 0, spin 1, spin 2, spin 3, etc. These are bosons, and these can have more than one, these can share a state, And then there's fermions. These have half-integer spin. So 1/2, 3/2, etc. So things that are bosons are things like the photon is a boson, whereas things that are fermions are things like electrons and protons. Those are fermions. And the Pauli exclusion principle, which is a result of the interaction of quantum mechanics and relativity, the Pauli exclusion principle tells us that fermions cannot share states. Right? Once you have a particle in a particular state, no other particles can share that state with it. No other fermions can share that state, but bosons can have as many in a state as we want. Another way that we could represent this that will be sort of relevant to the discussion is we could also represent this as a grid. So we could say 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Those are the different states. And we could plot on one axis the states of particle 1, for instance, and on the other axis 1, 2, 3, 4, and 5. These are particle 2. And first of all, what we can see is that if the particles are indistinguishable from one another, that there's no difference between 2, 1 and 1, 2, that these are the same state. So we can see we got to get rid of all these over here, because those states that I've just cross-hatched out, those states all exist down here, right? And these, which I'm sort of outlining in red, that's fermion land, whereas the diagonal elements, those are elements which would have two particles in the same state. Those are only accessible by bosons. So the diagonal elements, there's 1, 2, 3, 4, 5 of them, are only allowed for bosons, whereas the others, the other 10 here, are these states over there, which can be occupied, or can be valid for both bosons and fermions. So the distinction between bosons and fermions is where these diagonal elements, whether those diagonal states there are allowed, or those diagonal situations are allowed. Now, if the number of states gets very, very large, and if instead of having 5 possible states for each particle, if we have Avogadro's number of states for each particle, then the edge condition where bosons are allowed and fermions aren't is going to be a very, very, very small part of the entire area of phase space that's allowable by either. So when the number of states is large, it doesn't really matter if you're a fermion or a boson, because again, if the number of states is much, much larger than the number of particles, the probability of any two particles even trying to occupy the same state is so minuscule that it doesn't even ever enter the conversation, or the calculation. But if the number of so when the partition function for single particles is much larger than the number of particles, then we don't have to worry about whether or not the edge conditions are important there, whether or not it's a fermion or a boson. But when we start to get close to filling all the states, when the number of particles is of the same order of the partition function for a single particle, then we have to worry about being in the quantum limit, and it matters whether or not we're bosons or fermions. All right, so how are we going to deal with these crowded states? Well, the answer is we do something very, very clever, which is that instead of thinking of our system as being the particle which then occupies a state, we think of our system as being the state. Each single particle state becomes our thermodynamical system, and that then has a state, the state has a state, an occupation of that state. So we keep track of the occupation of a state as if it was the energy of the state, or the state itself, and then we our system becomes the whether or not a state is occupied. Our system becomes the state. Boy, this is a little bit it's not as complicated as it sounds. It's very much like how we treated, actually, the hemoglobin situation. We thought about the site as our system, the hemoglobin site as our system, which could then be occupied by nothing, or by an oxygen molecule, or by the carbon monoxide molecule. Here we're going to do the same thing. Our state, whatever it is, could be occupied by nothing, or it could be occupied by one or more particles. And because we were very, very general with how we defined things when we laid it out for the Gibbs factors, it turns out that none of that particularly depends on whether or not our states were localized to individual positions in the universe and things like that. So the probability then becomes the probability of our state having occupation n, and that's going to be 1 over the partition function times e to the minus number of particles times the energy of that state minus the chemical potential times the number of particles over kT. So 1 over the partition function times e to the minus n times energy minus chemical potential over kT. And for fermions, n can only be 0 or 1, because those are the only two occupations we allow. So our partition function then just becomes a very simple truncated sum, 1 for the case of 0 occupation plus e to the minus energy minus chemical potential over kT. So this is the empty, and that's the filled condition. And since we know our partition function, we can then calculate the average occupancy. That's going to be, take a thermal average, so average over the occupation times n times the probability of having an occupation n, which in this case is going to be 0, the number, times the probability of having occupation 0, plus 1 times the probability of having occupation 1, or in other words, our average occupation is just e to the minus energy minus chemical potential over kT, the Gibbs factor for the filled state, divided by the partition function, 1 plus that very same Gibbs factor. This is a form that looks like e to the minus x over 1 plus e to the minus x, which if we multiply top and bottom by e to the plus x, gives us, well, the plus, that just gives us a 1 on the top. This 1 becomes an e to the plus x, and then the e to the minus x times e to the plus x just becomes 1. So we can rewrite our distribution in its standard form here, that the average occupation is just 1 over e to the energy minus chemical potential over kT plus 1. And we call this the Fermi-Dirac distribution. And it tells us the relative, it tells us what the average occupation for a given energy level or a given state is likely to be. Here is plotted in your text the Fermi-Dirac distribution on the vertical axis versus energy, where this midpoint here is the chemical potential for our state. And you can see that at high temperatures, you get a relatively smooth transition from full occupancy, probability very likely to be 1, for very low-lying states. So low energy states will be completely full, and that will gradually drift down to 0 occupancy for very high energy states, and the midpoint of that changeover will be this point of the chemical potential. And if the temperature is high, that's a pretty smooth turnover, whereas if the temperature is low, that's a very sharp transition. And indeed, at 0 temperature, what you get is that everything up to the chemical potential here has occupation 1, and then it drops instantly down to occupation 0 everywhere above the chemical potential. For bosons, the situation is slightly more complicated, but not too bad. All right, so for bosons, n can be any non-negative integer. So 0, 1, 2, 3, etc. And so our sum here has to go over more than just 2 terms. Our partition function then becomes an infinite, or essentially infinite, number of terms. So there's the empty state, the occupancy 1 state, E minus mu over KT, plus an occupancy 2 state, which will be E to the minus 2 times energy minus chemical potential over KT, and so on and so forth. We can write these later ones as 1 plus E to the minus energy minus chemical potential over KT, plus that same E to the minus energy minus chemical potential over KT, and square that term, and so forth. So that, in other words, our partition function here is a sum from k equals 0, potentially up to infinity, of E to the minus energy minus chemical potential over KT to the kth power. So this is the geometric series here. So geometric series, a little bit of a reminder, k equals 0 to n of x to the k. Well, this has a solution, which is 1 minus x to the n plus 1 over 1 minus x. Now, if we want to let this series calculate with an infinite number of terms, and yet we still want it to converge, well, x to the infinity is obviously not going to converge unless x, or the absolute value of x, is less than 1, right? So we have to let our x here have a value less than 1 so that x to the infinity will go to 0, and this will converge. In our case, our x is e to the minus epsilon minus, or energy minus chemical potential over kT. Well, e to the minus this, e to the minus something is a fraction less than 1, so we're fine as long as energy minus chemical potential is positive, right? So this will only converge when energy is greater than the chemical potential, and if it's not greater than the chemical potential, then this sum will diverge. We'll have an infinite number of available states. So for bosons, the state energy always has to be greater than the chemical potential. Anyway, we can then use this solution to say that our sum here, our partition function then, which was the sum k equals 0 to infinity of our Gibbs factor to the kth power, we'll just have the solution 1 over 1 minus e to the minus energy minus chemical potential over kT. Then we do the same thing. We calculate the thermal average occupation. That'll be n times the probability of having n. And so again, that's 0 times the probability of having 0 occupation plus 1 times the probability of having 1 occupation plus 2 times the probability of having occupation 2 plus ... and so on. If we do a label change here and call this quantity here epsilon energy minus chemical potential over kT, if we call that x, then this sum becomes the sum over n of n e to the minus nx over our partition function. We can pull the partition function out, so that's 1 over our partition function times the sum of n e to the minus nx, which is minus 1 over our partition function times the sum of the derivative with respect to x of e to the minus nx. Which means that our average occupancy is, again, minus 1 over our partition function times d by dx of the sum over n of e to the minus nx. So we moved the sum inside the derivative there. And that's minus 1 over the partition function by times dz dx. And so our partition function here, which is 1 over 1 minus e to the x we're going to write that as 1 minus e to the minus x to the minus 1. So that then our 1 over partition function here minus 1 over our partition function is just minus 1 minus e to the minus x. Okay. So just rewriting things, our derivative term here, so the derivative of our partition function with respect to x is going to be minus 1 minus e to the minus x squared. So that, or sorry, to the minus 2, not the squared, to the minus 2. So take the derivative of this, pull the minus 1 down, you go to the minus 2, and then take the derivative of the inside, which is e to the minus x. And so plugging this together, we have that our average occupancy here is 1 minus e to the minus x negative that times the negative, so this negative is going to turn that into a positive, 1 minus e to the minus x to the minus 2, and then e to the minus x. So the e to the minus x to the minus 2, this gives us 1 on the bottom. So this turns into e to the minus x on the top, and 1 minus e to the minus x on the bottom. And again, if we do the multiply by e to the x on the top and the bottom, what we get is 1 minus e to the x minus 1. So that in other words, our average occupancy is 1 over e to the energy minus chemical potential over kT minus 1, which we call the Bose-Einstein distribution. And so these two distributions, the Bose-Einstein and the Fermi-Dirac distributions, these are the average occupancy in thermal equilibrium for fermions and bosons, or Bose particles, respectively. And they differ merely by the +1 for fermions and the -1 for bosons over there. If we look at the limiting behavior of these two distributions and indeed compare it to the Boltzmann distribution, well, the Boltzmann distribution is the one where the chemical potential doesn't really matter so much. And we can see here, whoa, camera's freaking out. So what we've got here is a plot of the Bose-Einstein distribution, the Boltzmann distribution, and the Fermi-Dirac distribution in terms of average occupancy as a function of energy for the state. And what we can see is that the high state level, when the states are way, way, way high energy, all of these things drop down to be the same thing, right? So the high energy limit for the occupation of all of these goes to 0, and indeed over here those three distributions are indistinguishable from one another. As we go to low energy states, fermions will pack the low energy states up to almost 1, right? So you'll have essentially complete occupancy of low-lying states. For Bose-Einstein, instead of going to 1, what happens is as you approach the chemical potential, as the energy of the state approaches the energy of the chemical potential, the occupancy runs away to infinity. In other words, as you get closer and closer to the ambient chemical potential in our environment, bosons like to all occupy those states at right at the chemical potential of the environment, and they like to occupy it essentially infinitely. All the bosons in your system want to sit right there as close as possible to the state which is closest to the chemical potential of your environment. How does this work? Well, if we think about the chemical potential being the energy required to generate a particle out of thin air, and the environment has a certain chemical potential available to it. So you can pull as many particles of chemical potential mu out of the environment as you want. If there's a state near the chemical potential of the environment, that state will pull enormous numbers of particles out of the environment into that state. So that particles will try and glom into this state which is very, very close to the chemical potential, and the occupancy of that state will get enormous. The bosons will all stick together as if they are in the same, or to be in the same quantum state. And this is where you get superfluids and superconducting materials and things like that from. All right. Next time we will look at the behavior of some systems, and particularly we're going to look at Fermi gases in the degenerate state. So in the state, or in a state where most of the energy, most of the available levels will be filled. So we're going to look at an extreme quantum limit for fermions next.